All right, physics. We are moving on to chapter 16. We are looking at light, and we're going to start off with some fundamentals of light. All right, so let's see how this goes. Okay, so first off, light. So basically what light is it's a range of the electromagnetic spectrum, okay, electromagnetic waves, and it is a range of wavelengths in which our eye can see. Because there is a huge range of wavelengths which are electromagnetic, X-rays, radio waves, all those are electromagnetic waves. But there is a range of wavelengths in which we can perceive as light and colors. Okay? And depending on their wavelength, we can change the color of it. Okay? All of these waves, radio waves, X-rays, gamma rays, they all travel at the speed of light, and they do not need a medium. So they can run through a vacuum there. But if they do travel through a medium, they do slow down. So the more quote-unquote dense a medium, the slower they could go. So theoretically, you could take light and slow it down to the speed of a car, which people have tried to do. I think they have succeeded. I'm not too sure. Again, physics isn't my main thing here. So here's your visible spectrum. We can basically see from colors from 400 nanometers to 700 nanometers. Okay, higher frequency is closer to your ultraviolet, which is more of the purple, while the lower frequency becomes more red, and it's more of the infrared. Okay, and you see the wavelengths measured in nanometers are there. So the bigger the wavelength, okay, it's hitting our infrared, and the smaller the wavelength is more of that purple. So if you take something, and there's something known as redshifting, and it is when light is essentially pulled back and it's slowed. And so you take something that is a color, let's say it falls into the let's say it was originally yellow, okay, but you have something pulling it back, gravity, a black hole, something like that. And what it does is it pulls it back and it stretches out those wavelengths, lowering the frequency of it, because if the wavelength's longer, they're all going the same speed. So a longer wavelength would mean a lower frequency. Pulling it backwards and creating it a red color, a red shift. So things out closer to a black hole usually are shifted towards the red side because gravity is pulling them and stretching out their wavelengths. Okay, but that's your visible spectrum. So all the light you see, everything you see, basically falls between those. Okay, so this is just a quick, just images with it. So it shows you the wavelengths. So you see bigger wavelengths like radio waves are fairly large, microwaves, and then it goes to infrared, and then it's your visible light, and then ultraviolet, X-rays, and gamma rays. Okay, so from there. And this bottom bar right here is kind of what they look like. So like radio waves we can't see. Microwaves we can't see. Infrared we can't see unless we have a special tool. Same with ultraviolet. We can see them with that. X-rays, gamma rays we also can't see. Okay. And you see here the bigger wavelengths goes red, and then it shifts all the way down to purple. Okay, or red to violet. This top one is telling you if it penetrates Earth's atmosphere. So like radio waves can, when it's kind of between radio and microwaves, it's kind of hazy. Around this microwave section, it cannot. And then yes again. And then the X-rays, gamma rays, our atmosphere protects us because there's a whole bunch of stuff floating around in space that would probably kill us if we were out there. But our atmosphere protects us from it. Okay, doesn't let these evil gamma rays turn us into, the Hulk or something. Okay, traveling light. So light travels in a straight line, always in a straight line, if it's in a vacuum or if it's in a constant medium. So if it's in our atmosphere, if it's in oxygen, it's going to travel fairly straight. Now, slight changes in that medium, and it does move back and forth with reflection, refraction, and everything, but it's not going to be a huge change. Light is sometimes known as a ray, so it acts as a ray and a wave, and so those are known as ray optics. We're usually treating light here as a wave in this section. We're not going to treat it as a ray so much, but it is also a ray because light is one of those things. Okay, so let's talk about the speed of light real quick. So way back in the olden times, they thought it was instantaneous. So you turn on a light, everything lit up. They thought light was instantaneous. If you create a light source, instantly everything lights up from it. Okay, it doesn't have a speed. It was just instant. Okay, well, some people, Galileo, Mr. Troublemaker over there, thought that it wasn't. Okay. Now, here's the thing with Galileo is that, yes, he thought that it wasn't instantaneous. But the problem is that when you lived way back in the day, it's hard to prove something like that. Okay, which is sad. And so he would use an experiment where him and somebody else would be on two opposite mountains, okay, or two opposite hills. They would turn on a flashlight, okay, or they'd shine a light, and then when the person saw it, they shone a light, and then by the time you would basically time it from the start to the finish, and he wasn't able to show that it was any speed besides his the reaction time, because everybody reacts to it at a certain speed, and the time he got, basically he could have counted for, well, it was reaction time of one person lining up, second person lining up, me seeing it. So you've got 3 reactions there, and that adds up. Okay, so Romer, he was the one that really proved that it had a finite speed, that light had a finite speed. And the way he did it was that he took Galileo's idea of, measuring it from here to here, but instead of using it from, hill here to the hill on the other side of town, he used even larger distances. Now, the problem with Earth is that Earth is a circle. I know I might say something controversial there, but it's a circle, and at a certain point you can't see anyone because of the curvature. So, if you can't do it on Earth, where do you go? Way out in space. Okay, so he used Jupiter. Okay, so he used Io, actually, in particular, for it. And what he did was he kept measuring a moon of Jupiter and seeing when the moon of Jupiter would appear, Io in particular. And at this time they knew, because of Galileo, they knew how the Earth revolved around the sun, and there's times where we were moving this way and we were moving that way and everything, and they can do that with all the stars. So none of that was anything crazy. So what he did was he went, okay, when is Io appearing? Because if light was instantaneous, then the second that light hit the moon, we should instantly see it. Okay? But as he measured it, and he noticed that there was a 14-second window in both directions. When we were moving away from Jupiter, it took 14 extra seconds. When we were moving closer to Jupiter, it was 14 seconds quicker. So there was a slight change in that, and it should have been instantaneous. There shouldn't be that if it was instantaneous. So because it was 14 second change, he basically said it's not instantaneous. There is a speed. Okay. And so his conclusion, because of this, is that when we were moving farther away, it took longer because we were farther away from it, which means that it has to have a finite distance. So he did some maths. Okay? He did some calculations. Wasn't instantaneous. And he calculated that it would take light 22 minutes to travel the orbit the diameter of our orbit. So from one side of our orbit to the other, he said it would take 22 minutes. Okay. He also said it would take less than a second to cross Earth, which, you know, he was a little bit off. His prediction was that it was about 2.2 times 10 to the 8th meters per second. So that's how fast light is. Very, very fast. Okay. That's 220 million meters per second. He was a little off. The actual speed is 29979 to 458 meters per second after, and this is, you know, when we have better instruments and everything, and we're able to find it. So that's the actual speed of light rounded. I'm sure there's a decimal in there. But what we will use is that we will use 3 times 10 to the 8th meters per second. We'll just round it because it's going to be easier than trying to type that long number in. So we use 3 times 10 to the 8th meters per second. Okay, but him way back in the day, 1700s or something, was, you know, fairly close. I mean, 22 or 2.2 out of 30. I mean, he's off by hardly anything. So he was just a little bit. Okay, so that was a little background about the speed of light and everything. So now let's talk about just some of the key things with light. So sources of light, basically light can be not created, but light comes from 2 sources. One is a luminous body, which emits the light. Okay, emits the light waves. That would be suns and your light bulbs and anything, a flame. Okay, they emit the light. They basically have created the light, and it comes out. Okay, so that's a luminous body. An illuminated body is one that reflects it. Okay, so our moon is one that we see all the time, and a mirror is another one that's really easy. If you just take light and you can move it back and forth. But the moon is basically reflecting the sun's light off of it to us, and that's why we can see the moon. Okay, because it's the sun reflecting off it. The moon doesn't glow itself. The moon is not a luminous body. It is an illuminated body. The moon is lit up, okay, by the sun. All right, luminous flux is the rate in which light is emitted from the source. Okay, so when you see that, it is measured in lumen, or LM. Luminous, which is illuminance, which is E, capital E, is the number of lumen per square meter. And that is found in lux, Lux or Lx. Okay, so luminous flux is the rate in which it is emitted. Okay, measured in lumen. And illuminance is basically how lit is this area. Okay, and that's your illuminous. Lux. All right. Luminous intensity, okay, that's measured in candelas, whatever. Candle power, CD. Okay. It is the luminous flux that lands on 1 square meter. Okay, and it's basically found, like 1 candela is the light from it from a 1 meter sphere away. That's kind of like how it's found, but it's not really anything too crazy. But it is the amount of luminous flux per 1 square meter. All right, so formula. So the luminous, which is how much, how bright something is based on an area, is equal to the luminous flux. So how much power is being produced by this this light source, all over 4 pi times the distance squared. Okay, which is your basically the length from the light source, how far it is. And we want to be 1 square meter away, and so you measure it if it's the volume of it, or the surface area of it. And if you know what the surface area of it is, you can basically take this is how much is produced, divide it by the surface area, and that's going to tell you how illuminated each square foot is in that sphere. All right, so example, student's desk is 1.5 meters below a 1,750 lumen incandescent light bulb. What is the illumination on the desk? So basically, how bright is the desk? So we take our numbers. We take how much power is being produced by that lamp, which is 1750. Divide it by 4 pi 2.5 squared, and we get our answer of 22.3 lumen per cubic meter. Okay, because we're essentially talking about the volume of it, which then is our lux. Okay, so lumen per cubic meter is our lux, and so we would say it's about 22.3 lux. And so this makes sense because as your distance increases, what happens to the E value? If D keeps getting bigger, the E gets smaller. If you take a light and you shine it close to your desk, light on your cell phone, turn it on, put it close to your desk, and you can see it. Now, as you move it away from it, what happens? It doesn't get as bright because the light is being basically diffused out into a larger area. And because it's a larger area, you only have a certain amount of power, and so you don't get it as bright. All right, that's the end of section 1 of chapter 16.